So hey guys, today we are going to start with yet another research paper, that is selective attention improves transformer. So from the name itself, it's pretty clear that we are going to do some modification in the attention algorithm. Now we need to figure out what we are going to do and how is it helping us, right? That's the purpose of reading this research paper. So this research paper, selective attention transformer, was released by Google on 3rd of October 2024. That is around 16 days back from the time I am recording this video. Cool. So I figured out some important points in the paper that I have already highlighted. So we are going to go one by one through them. So from the name itself, that is selective attention. It's pretty clear. We are not going to focus on everything, but some selective parts, right? So in unneeded elements in the attention's context degrade performance. This line itself makes it very clear that okay, what this paper is going to be about, right? So they say we introduce selective attention, a simple parameter free change to the standard attention. Cool. Mechanism which reduces attention to unneeded elements. So what they are saying, not every relationship or every context need attention when you are working really with the long context thing, right? And you don't want things which are unused or they are actually not making sense sometimes need attention at that point, right? So we are going to see some good examples which the paper also mentions throughout the reading part. So if you give it, they are saying, can we design a model that persists just the right amount of context? That's the main point, right? Because they are saying different tasks have different type of memories. On one extreme, copying an sequence requires retaining all sequence elements in the memory. But on the other extreme, determining whether a specific element appeared at least once only requires persisting a constant amount of memory. It's 100% correct, because if you guys see, when we have multiple elements, right, now the relationship between two elements cannot be just defined using the context between both of them, but also figuring out that what these both mean to each other, right? So in the work, we propose selective attention, a simple extension to the standard attention mechanism which allows a token to decide that other token is no longer needed, reducing the attention that future tokens will pay to it. So yeah, this line also makes sense. Now what they say here, that selective attention allows adults to focus on task relevant information while ignoring task irrelevant information. This in turn leads to superior processing of task relevant information. So this they are telling from a real life thing only, because if you see, right, from the name itself, selective attention, you want the model to focus on things which are actually task relevant information, not the ones which are task irrelevant, right? So when you do this, you're not only focusing on the important one, but also ignoring the unimportant one, right? Now, one very good example which these guys are mentioning here is, if you read this, suppose you have a given layer, right? And now you want that there is a token B, right? There is a token B, and then there is token A and C. Now, B can decide how much to read from A, right? B can decide how much to read from A, and token C can decide how much to read from token A, right? But this particular token, the current token, I'll change the color. Yeah. So this particular token B cannot currently decide that how much token C reads from A, right? B cannot affect this thing. Now, specifically, even after knowing the fact that B has already determined that token A is sort of irrelevant or even misleading to the future tokens such as C, it's of currently no use, but still token B has no power of deciding that thing. So there is nothing it can do in the layer given to correct this. So what they're saying, even in the masking part, right? Even in subsequent masking layers, masking token A is not trivial, obviously. Then selective attention enables exactly such masking. So this problem that we are seeing here, it is going to help us solve that. So they have given this wonderful example of language modeling. You can see here that how soft masking by selective attention and attention strength, but for different tasks, is actually impacting the whole role, right? If you see here in the variable assignment also, same thing is happening. If you see the red lines and the blue blocks, you will be able to realize that, right? Similarly, in the language modeling part, you can see that. Now, in this example which they have said, that suppose for the input y is equal to 7, x equals to 1, x equals to 3, z equals to 5, what is going to be x? The output is going to be 3, obviously, right? So here you can see the generation, it's a sort of a search problem, right? This repeated occurrence of the query pattern are allowed, and when we are tasked with finding The most recent ones, it is well known as the search problem is easily solvable by standard transformers by induction heads. So things are actually already there, but we just need to figure out how we are going to do that, right? Because if you currently see, this problem has been in the play for a long time, but realizing that, okay, this impact which B can create by allowing C to know how much A is affecting, that is going to help us a lot, right? Similarly, if you see the after a variable problem, the language modeling part, that the sequence Barack Obama, the first token bar encodes several competing meanings, right? But the later tokens AK and Obama resolve it to be the entity for ex-president. You can see here. A day after former president. Now if you see here bar, so you see the relevance of this bar is coming from the previous word former president, else it doesn't has that relevance, right? But these words after, does it play a role? Does it play a role in deciding what does bar or like Barack has to do with the former president? Does it has? Then now I'll leave it to you guys to decide, because I have already told you an example, right? What I'm talking about here. So is it impacting these words? These words are impacting the other ones. Obviously they are impacting, right? But the relevance, it's not that much. Now, similarly, when it comes to selective attention, now coming to the mathematics, what they have done. For context size n, we are producing a real n by n value, or soft matrix S. So let's keep things very clear. Keep things very clear. I'll write down the current formula of attention, right? Because then we can actually compare side by side that how both of things are different with each other, right? So what is the current formula? See, this you have the softmax. You have the softmax, right? Then you have the query, the transpose of, right? And then you have the underscore D, right? And then you have the value. Simple as that, right? Now, how the current one is different from this currently? You say only this f variable which is there, right? This f variable is the new one, because this you cannot find here. So this subtraction of f variable, whatever this is right now, is going to make all the difference. So we have figured out what is selective attention sort of here. We are making a small change and it is helping us a lot. So let's go through it now. The mathematics is not at all that tough. So stay with me if you guys are not sometimes not good in reading that much mathematics in a paper. So let's say we have context size of n, right? We are producing a real n by n softmax matrix X. Okay, so we have S matrix here, where every time this token Xi masks token Xj. So we have this matrix, right? And you have that Ij here, so 0, 1, 2, 0, 1, 2. So it's pretty clear that this is masking this one, this is masking that, right? So, and at the very end, we then constant S. Example, they are saying that to be casual and non-negative, the section 3.2 we are going to look in detail. And then we finally accumulate the information in matrices into a new matrix F. So we are going to sort of do, the cumulative sum that we do. We are going to talk about that in the coming section. So what is matrix? What is this? This is the cumulative sum of constraint of S. Simply subtracting from the attention logics before applying the softmax. So not at all hard. We just need to figure out how we are going to calculate this F, right? Cool. Now, if you go here, they are saying that this current paper, I would recommend you guys to go and read. It's about speculative decoding, and it will help you a lot if you guys don't know about masking and like how things work at the back end of a model, right? So yeah, it will help you a lot. Now they are saying that computing the matrix S is akin to computing a compatibility score, and many functions can be used, right? There will be a separate Boolean form that they are saying. Now they are saying, following an observation they are getting from this paper, a common case for token wanting to mask another is after absorbing its content. I think if anyone has gone through the paper or even the similar papers, they will get to know this point, right? We instead simply reuse the result of one of the existing heads of the attention module. So this means the selection function adds no new parameters or computation. So note that the head still contributes to the attention as usual. So this is a very important section. If you understand this one, there's nothing like much left to talk about. Now, after getting the observation from the paper, they are applying the following to the constraints to S, right? First is zero out the negative values, only reducing attention, never boosting it. That is applying ReLU, right? Now, zero out the first column so as to not mask the BOS token, obviously. Now, zero out the diagonal so as to not let a token mask itself. So I think if someone has gone through the paper, you already know that these 3 points, like at least two of them, everybody knows, Third one also, I think most of the people know these constraints, right? So we have decided this on the basis of this, and I personally think while after applying this part, this accumulation part is not that tough. If you come here, they are saying we observe some improvements by only applying the mask for future tokens, right? That is, masking by a token would not affect its own attention operation. So yeah, accumulative sum. So I think most of you guys already know what cumulative sum is, but for people who don't know, a very simple example goes something like this. Suppose you have an array of, okay, I got the pen. Yeah. Suppose you have an array of 1, 2, 3, 4, right? Now, the cumulative sum goes something like this. If you can see here, they have this np.cumsum, and this is going to be np.array obviously, but for the example I'm telling 1 obviously, then you have the second element as 1 plus 2, that is 3. Then you have 3 plus 3 is equals to 6, and then you have 6 plus 4 equals to 10, right? So it's a very basic, simple mathematical operation. So yeah, that is cumsum for you, right? So you have got the logits, you have applied the ReLU, you are not masking the BOS token here, you can see, and you are not masking itself also, here you can see, and then you are masking strictly in the future, and then you are going to accumulate it, right? Now you have got the attention logits and the softmax of attention logits. Simple as that. So you are subtracting it from the main one, attention logits minus f, that we were seeing above. Wait, yeah, here we were seeing, right? This is what you are going to do. Simple as that, not that tough, right? Now coming to the context tuning part, I will recommend you guys to go and read this, because it is sort of telling you that how once a token is sufficiently masked by selective attention, it will not contribute meaningfully to any other future attention operations, right? Such tokens can be safely evicted from the context buffer. So they are saying that they have picked up a buffer, let's say k, and any soft masking that is, let's say x, which is higher than k, right? Which is higher than k, but that would make the memory obviously savings to hard take advantage of. So instead, they will observe that sparsity per layer is stable across the samples. So they have decided that threshold point, and they are going to prove all the elements, let's say x, which has greater value than k. So yeah, this threshold they have picked up, right? Now, similarly, they have all the mathematics for this here. This is also not at all that tough. So yeah, I think we can move to the next part, which is experimental setup. What they are saying that the layer normalization part, they have used pre-layer normalization instead of post. From the paper they have mentioned, they have used learned position encodings. They have used Swigglue instead of the MLPs, right? And they have normalized the Q and K projection, the query and key, and they have removed the biases and replaced the layer normalization with RMS. So yeah, they have made some changes, but what they are saying in the next line itself, that we tested other variants, including a vanilla decoder transformer, and observed similar results. So that is also fine with that. They have used a cosine decay, 1000 linear warm-up steps, and a learning rate of 0.05. Cool. They have, experimented with different learning rates and observed similar results, they are saying. So sort of what they are saying, that we have already tested with everything that was possible, and we see similar results. The parameter, that the dimensions of the model, they are 60/40, and the number of heads and the number of layers remain the same, equal should be. So they have trained the models on TPU V-Force, and we can see the vocabulary size here is 8k tokens, right? And they have used the sentence piece tokenizer. So they have kept things simple. That's good. They have also came up with some experiment of size 32k of the vocabulary, and they have still absorbed similar experiments. So that's good, because they have mentioned that, it's not like that we are only working on this particular part, but we are working on a lot of different things, and we see similar results. On the results, it's simple as that. If you see here, the validation perplexity. So I think I have already told a lot of time that what is perplexity, but when I am talking to a lot of NLP folks, I realize that perplexity is one topic that people don't pay that much attention to. So what is perplexity? I'll write this down. Perplexity, right? So perplexity in a single line is sort of a measure of uncertainty. Simple as that, nothing difficult, right? Please ignore my handwriting. It's hard for me sometimes to use these digital pens. To be honest, I personally think that this perplexity part should be known by everyone when you're working on any project, because it is sort of, if I want to tell you in a nutshell, a measurement that how well a distribution or probability model predicts a sample. So let's take an example. So let's say you have an entropy of 3 bits. Okay, I'll put a different color and write this down. Cool. So let's say you have a 2 raised to the power 3. Okay, so you have 3 bits in which each bit encodes 2 possible outcomes, right, of equal probability. So this means when predicting the next symbol, you have 2 raised to the power 3 possible outcome, that is 8. Okay, so we can argue obviously that language model has a perplexity of 8 here. So what is the overall basic PPL, that is PQ, and that is 2 raised to the power H probability factor that you have, and Q. Cool. So this is the formula of perplexity, and I think this is sort of related to entropy if you guys have already read about it. So it will become easy for anyone to understand if you have a background in that what is entropy of a language. So let's say the language is translated into binary digits like 0 or 1 in the most efficient way. The entropy is the average number of binary digits that are required for a let's say letter of the original language. So yeah, that's entropy. So yeah, moving to the results, we have the context length, the model parameters, and in all of the results you can see figure 3 that they are saying left compares the validation perplexity for casual language modeling on the C4 dataset for decoder D is equals to 12 transformer models with and without selective attention, and we can see the results going better obviously in the case of validation perplexity and context length for selective attention. Here you can see a very major difference we can see. Similarly, if you look here, you will see a very skew difference, but there is a good difference if you compare it in the model parameters for selective and non-selective attention, right? So we can clearly see a good difference. So it works for us, right? Now they have also compared the accuracy of transform of different sizes with and without selective attention. So let's see. If you see at dimension equals to 16, this is one. Almost every time you will see there is a significant difference, not that much, but there is a comparable difference here. Because what I think is that even if there is a 0.5 difference, right, 0.5% difference, that is something that have come out of a new way of transformers working internally. We have decided, right? Similarly, if you see, we can see some huge differences also. You can see here a difference of around 1.17%, right? So here you can see a difference of around 2.6%. So it's not like that we are working on in particular one dimension they are saying, but we have worked on multiple dimensions and then we are coming up with this conclusion. So if you can see this attention parameter log also, you'll observe that the validation log perplexity is still the best for attention, right? Selective attention part. So inference efficiency, they have already talked about that efficiency improvements through selective attention stem from reduction in the attention's module context size when using the prompt pruning as in section 4. So I think pruning, most of you guys know that we work on a set of layers. So pruning is one concept. If I was working previously when I was working on this LoRa and QLoRa, and then I got to know, okay, what is this pruning? And when I got to know about that, it felt really good. That is a concept that I think every NLP engineer should know about, right? So you also, they are saying that indeed note that during inference with a large context and batch size, loading the KV cache dominates and the memory bandwidth, which is often the bottleneck for generation. Cool. So I think they have mentioned most of the things here. So this is an important section which I think you guys can go and read. I'll try to keep the video as short as possible. And then you have the selection parameters. That is also something that you guys can go and read. The context pruning they have done, the related work, transformer improvements, attention modification, context pruning, and inference efficiency. That are the 3 main things that we have discussed in the paper throughout. And the limitations and future direction, they say that they have applied attention to decoder only transformers. It would be interesting to investigate its applicability to encoders as well. So this is going to be interesting. Actually, this is going to be interesting, and I'll be waiting for these guys to come up with something if they see that, okay, there's some improvement. We did not further train the models after removing elements as per section 4. It seems conceivable that further improvements could be achieved with some additional training after context detection. Okay, so we have something for the future here, right? And we all only experiment with pre-training models with selective attention. How it could be applied in a fine-tuning step to existing models. And that was, I was reading throughout the paper and I was expecting something out of this, because nowadays everyone wants to do this, right? Now, improving neural architecture, they have written this whole thing that in the art of transformer programming, selected at foundation models and manually implemented transformer to solve them, right? So yeah, cool. Now you have the appendix section, and in the appendix section, we were talking about the A6 thing, I think. Yeah, the perplexity inference trade-off you can see here. So this diagram is sort of in a nutshell is telling that how perplexity and efficiency were a trade-off for this current selective attention part that we were doing, because when they say this illustrates the trade-off between perplexity gains and efficiency gain when pruning, as in section 4. So yeah, because see guys, one thing is pretty clear. When we comes to inference is the most important part, right? Because if you are not able to get a good trade-off in that, then the whole part when it comes to accuracy will feel a bit low. So yeah, that is important. So for people who don't know that, this KV caching and everything, I have made separate videos on this. So you guys can go and check that out. Now, I think most of the time when I said pruning, everyone knew about it. But pruning in language models is a technique, used to reduce the model size by removing the less important parameters. You're removing the less important parameters. I have been talking about this for 15-20 minutes. So I think everyone knew about it, but okay. Parameters, right? So yeah, I think most of the things are covered here, and you can see the following text from C4 validation was used in figure 9 and 10. So yeah, I'll be skipping this because video is already about 20 minutes. So I'll try to keep this short. So overall, it's a really good paper, guys. I would recommend you guys to go and read this. The mathematics in this is also pretty easy. You will be able to understand it. I hope my explanation was contributing to you guys understanding that mathematics for this paper is not that complex. So yeah, let's next time when we'll meet, I'll come up with a different paper, maybe about differential transformer, something like that. So yeah, thank you for watching the video, guys. Thank you and have a nice day.